Hello my friends, my name is Fyodor, and today I will tell you how to create an IoT cluster by using ASP.NET Core and a library for it called SignalR. The main purpose of SignalR is to abstract away programming complexity of WebSockets protocol. WebSockets is an ideal protocol for IoT devices, and the reason for that is because it allows you to communicate two ways between client and the server. You don't need to get your client to send a request to the server before you receive the response. Server can initiate communication too. But the specific thing I will be focusing on in the video is to how to get your IoT devices to act as a single cluster, as if it's one big device. And as you will be able to see in a minute, there are many real-time applications for this. But I will show all the general principles behind it in the code. So in our example, imagine a situation where we have a server and we have 4 IoT devices which belong to 2 distinct groups. Each one of those groups can represent, for example, a train station, and each of the devices is located at a separate platform. Each one of those locations is a distinct IoT device cluster. All devices in that cluster know of each other. And let's imagine the situation where the train is about to arrive, and one of the devices is given a command to play an announcement. And then, while the first device is playing the announcement, the second device is given the same command to play one for its own platform. Because both of them are located within the hearing distance of each other, if they know of each other, then the second device will not start playing its own announcement until the first device has finished. And this is the principle we'll demonstrate in here. So in our initial setup, we have 2 applications. One of them is ASP.NET, server-side, and the other one is a simple console application which will go onto IoT devices. Both of them at the moment are using .NET 5. So in our ASP.NET application that goes on our server, we've got basic SignalR setup. We have devices hub endpoint, which we associate with devices hub path in the URL. Our devices hub has 3 methods. Receive device connected, which is being called by any IoT device that gets connected to it. Broadcast work status, which allows devices in the same group to talk to each other. And on disconnected async is override method, which is being called whenever the device disconnects. When our device initially registers itself, it sends 3 parameters: device ID, which can be serial number or a host name of device, area name, which will then be mapped to a SignalR group, and location number, which is an arbitrary location identifier. What we do first is map device ID to a SignalR connection ID, which is arbitrarily generated by SignalR. So we can associate a human-readable identifier with the one that SignalR has created, which would normally be GUID. Then we map our device to a specific location, which is also mapped to a SignalR connection ID. So basically, anywhere in the server we can just say, send signal to this specific location, and our system will know that what it means is this specific connection ID. And then, as I already mentioned, area name is a group name. Here is the code of our IoT application, which is fairly simple. We have this variable which is used globally, which is called hold of work, and it's false by default. First we have to type in the unique identifier. Then we need to provide the area name for the device. And finally, we need to provide location identifier for the device. Once we provided this information, the connection to our SignalR hub is established. Devices hub at the end of the URL is what we've registered here in the startup class. Once the connection is established, we associate certain events with it. So whenever our server calls one of our IoT devices, it's this logic that will be executed. So if our receive work method is being called from the server, do work method is being executed on the client side. And receive work status is something that we've seen in the hub already. It's the method that gets triggered by a client calling broadcast work status. And then all devices in the same group where the client device is get their receive work status event called, with the working status updated. So essentially, if the device that called this method belongs in the same group, every device in this group gets its hold of work variable set to whatever data has been received from the server. The method itself is called from here. Whenever a command has been issued for the device to do some work, before we start doing some work, we update this method with the status of true. So every single device in our cluster will receive this. Once we've finished, every single device in our cluster will receive false. In our case, we'll just simulate some work being done by just waiting 60 seconds. But here's how it works. When we initially enter doWork method, and if our hold of work is set to true, we will not be doing work straight away. What we will be doing instead is waiting until the other device has finished. One thing that is important is to make sure that there's some cutoff period as well, because we may lose connection, and this is why if we haven't received complete work flag in a certain amount of time, we automatically set hold of work variable to false. Let's have a look at our server code to see how this method is actually executed. We have this event scheduler class, which just keeps running, and it keeps sending commands to devices. We just assumed here that we have 4 devices, and that location of those devices are called 1, 2, 3, and 4. And all we do is just keep running it and keep sending commands to the devices. Those locations are mapped to particular areas. In our case, location 1 and 2 are mapped to north wing, while locations 3 and 4 are mapped to south wing. So if we go back, when we issued command to location number 1, it would automatically notify location number 2 that is doing some work. So next, when we call location number 2, it will wait until location number 1 has finished, and they just keep replacing each other like that. Same applies for location 3 and 4. So essentially, the devices at the locations 1 and 2 belong in one cluster, while the devices at the locations 3 and 4 belong in a separate cluster. Those two groups don't affect each other, but both devices in each group do affect each other. And all of this is made possible by the fact that SignalR is nothing but abstraction of a WebSocket protocol. Of course, it can use other protocols as well, but WebSocket is the main one. Unless you absolutely have to change it, it will be a WebSocket. If you don't know what WebSocket is, it's a protocol that allows client and server to communicate both ways. All the client has to do is establish the connection, and then that connection will be persistent. Once established, both client and the server can talk to each other. There is no need for client to submit a request to receive a response. The server itself can send messages to clients. And the massive benefit that is specific to SignalR is that it abstracts away all programming complexity of WebSocket protocol. Normally you would have to split everything into chunks of bytes, but SignalR abstracts it all away and makes it look as if you are calling methods on the client and the server directly. And this concludes our example on using SignalR to coordinate IoT clusters. This code is available in GitHub repo, and the link to that repo will be in the description to this video. Thank you for watching, and all the best.